Okay, let's conclude this little series of podcasts under evolution of carbon cycle and climate regulation with a couple of points. Obviously, we are worried about the future. That's the main goal of this course, is to set up carbon cycle and climate regulation context for the fossil fuel emissions and where we are headed as far as climate and emissions are concerned. This is a nice figure from earth.org which is showing carbon in parts per million by volume over time. So there are nonlinear scales, you have to be careful. So it goes back to about 400 million years ago when the ppm was over 2000, maybe even going up to 2500, which is much greater than anything we have seen for a long time, maybe even going back to 50 million years ago or longer. Obviously, then many people ask a question, why are we worried about global warming if it was already that high in the past? Of course, the first answer is that human beings were not around then. So obviously planet will stay and biology will survive. It's a question of which species won't survive, including us. And also because the second point is that the way we are emitting carbon right now, if we don't do anything, we could reach those levels by about 22 to 2300 AD or Common Era, basically because the carbon keeps accumulating. It's an inert gas with a very long time residence time scale of multiple centuries, so it's been accumulating already since the Industrial Revolution. So these are the various representative concentration pathways for the future of where carbon is headed, and the benign scenario here is about keeping the global warming target at 2 degrees C with a 66% probability or lower. But we already talked about all the processes, weathering rates, weathering feedbacks, oxygen, sulfur, iron feedbacks, degassing rates, reverse weathering, and so on, to go through these various levels of carbon dioxide in the past, and we will come to the temperature associated with these in a minute. But the evidences here are combined from stomata, liverworts, and paleosols. Paleosols, old soils that are able to be dated and carbon signatures gathered. The stomata and paleosols here, along with alkenones for delta C13 data is in here, and benthic forams are down here. So how far you can go back depends on, for example, if the ocean crust is always forming and being destroyed by subduction and so on, then you won't be able to go back too far into the past with ocean sediments. You'll have to find other rock-based evidence and so on. There's been a change in time scale along the way, which we will see in a minute. We have seen it before. But this stable levels of carbon dioxide for the last 20,000 years ago or so ago has obviously favored stable temperatures as well. So the CO2 is a key driver of climate and climate variability trend and regulation along the entire Earth's history, which is why we have to worry about carbon. To show another time series from a shorter period from Vostok ice core, this is going now back to about 800,000 years ago. This is the rapid deglaciation, which emits about 80 to 100 ppm back into the system, and the slow deglaciation, because as temperatures cool, glaciers grow. Cool temperatures make the atmosphere drier, snowfall rates fall, so the glaciers glow at a much lower rates, as we already saw. So we are in the warming phase now. That's why we have to worry about abrupt changes that happen during warming phase of these glacial interglacial cycles. And here we are going from 1950 level, which was still in the range of what was observed in history before humans started affecting things, to where we are now. Especially the rate of increase is not slowing down. So if we zoom into the last many decades, then obviously we are increasing CO2, but despite the negotiations and renewables and other technologies, there is no slowing down of the emissions, and accumulated carbon of course keeps growing, and the accumulated carbon determines the temperature warming rates as well. So this is what we are worried about. Associated with that, from Earth.org, this is the estimated temperature anomalies with respect to the 1960 to 1990 baseline. Obviously, when you had 2000 ppm or 2500 ppm CO2 in the atmosphere, you had very warm temperatures, no glaciation over Antarctica, Greenland, no ice over the Arctic, even back here during the time of the dinosaurs, during Triassic, Jurassic, Cretaceous, and so on. Again, the point to remember is that temperatures have swung around quite wildly in the past, but if you look at the fastest and the greatest warming that happened during the Paleocene-Eocene thermal maximum, then that warming is slower than what we are observing now because of human activities. But you can see the Pleistocene glaciation cycles in temperature as well as in CO2, as we saw before. The warming since the last ice age ended about 20,000 years ago led to the Holocene, where the temperatures have been fairly mild, which is where the modern human being, agricultural way of life, population growth, fertility rates increasing, and arriving to industrial revolution, and where we are now, all happened in this fairly benign range of temperatures compared to the past. So that's what we have to worry about, whether we as a species can handle wild swings of temperatures or not. Already there are many evidences that some communities, countries, and so on pay a heavy price. Eventually now every country experienced massive extreme events in the summer of 2021, for example. So rich countries are not exempt from the impacts of climate change already. The future growth here is better shown in this plot, which goes back only to about 65 million years ago, and it shows the same thing but now more expanded future projections starting in 2005, where we have arrived by 2021, and where we are expected to go by 2100, 2200, and longer. Of course, we have to be careful with these projections because the model uncertainties dominate the range of future warming depicted for next 10, 20 years, maybe 30 years, but after that, beyond about 2040, 2050, the scenario uncertainties begin to dominate the range, which means the assumptions made about population growth, technologies, renewable energy, carbon capture and sequestration, bioenergy, and so on, begin to provide the range. So one has to be careful because you can change the scenario and produce a different range of temperatures. So obviously that matters. I took the last piece of this and made my own little graphic going back to 500 million years ago. So you can see this nice long temperature record now with the wild swings, the cooling with the mountain building and reverse weathering that we talked about, Pleistocene glaciations, end of the last ice age, Holocene, and where we are headed into the future. This again goes to 2200 or so, so obviously we have to be careful, but it depends on how many generations into the future we want to worry about in terms of temperature warming, sea level rise, melting glaciers, extremes, and of course CO2 levels and pollution and so on. But worrying about the next 10 to 20, 30, 40 years is unavoidable because everything we plan in terms of infrastructure, energy grids, transportation, buildings, etc., depend on this kind of timing horizon. So we will leave this here to move into actual carbon capture, sequestration, and utilization ideas, the chemistry, the scales needed, amount of carbon needed to be drawn down to meet the global warming targets, and the difficulties of accomplishing these in terms of the scale, especially in terms of drawing down CO2 from the atmosphere, what is called direct air capture, because carbon in the atmosphere is only 0.04%. So obviously not at all easy to take out something at that small concentration, but many groups are working on this, and hopefully some game changer will come along and boom, we will have carbon being taken out and sequestered and magic will happen. In the meantime, we will leave this series of podcasts here and then move to carbon capture later on. Okay?